Welcome to the Combinatorics seminar. Today, we're happy to have Boris Bukh from Carnegie Mellon University, and he's going to talk about empty axis parallel boxes. Take it away from here.
Thank you. Thank you very much. So again, it's my understanding this is press seminar, so I'm not going to yet talk about empty axis parallel boxes. My plan for the press seminar was to just give some general, blurb about discrepancy theory. And then again, when the main seminar starts, I will talk about actual empty axis parallel boxes. So again, for both event parts, I want to tell, please, if you have questions or remarks or jokes, whatever, just unmute yourself and go ahead. I mean, I'm not monitoring chat. Again, just speak out. Okay. Okay. Good. So discrepancy. This is the game for tonight. So this the setting is this. So we've got a box, so a unit box. So this is, I will draw two-dimensional pictures, but everything carries on in higher dimensions equally well. So this is my picture of 0, 1 to the d. And I have a subset of the box. So it's a discrete subset. Actually, in fact, finite subset. So P is subset of 0, 1 to the d. And it's got, throughout the talk, we'll have n points. So n will be number of points in P. And what I want to distribute these points inside this box uniformly. I mean, I want to spread them fairly evenly. Okay. Question is, what do I mean by evenly? And of course, it depends on application, but the kind of application I think about today would require that, if I take some kind of ball, some kind of set inside a unit square, and I count how many points there are, it should be about the right number. Okay, so let me just write it rigorously. So I have some kind of set S, say inside the unit square. So now this is not a finite set. This is just, think about maybe a disk or a box or some kind of nice set. Okay, and I'm going to look at the points of P that fall inside S. So so let me just draw the picture. So I have some kind of, here is my set S. Okay, and by the way, you should be able to see things well with the current video setup. If it gets blurry or not or grainy, do let me know. Okay, there are some things I can tweak a little bit. I cannot guarantee I can fix things, but do let me know if you cannot read. Also, my handwriting can be bad. Do also say that. Okay, so I'm going to look at the points of S, H, and P. And intuitively, if my S is half of the box, I expect to get, well, half of the points of P. If my S is maybe a third of the box, I expect a third of the points. So let's compare what I do see inside S to what I expect. So what I do get inside S is this set, and it has this many points. On the other hand, I expect to get the volume of S. Okay, and again, in the case of the dimension 2, volume is the area, but I'll say volume all the time. So volume of S times the total number of points in P, which is, again, by convention is N. So there are two quantities. This is what I do get, and it's what I expect to get. And so I'm going to look at the difference between the two quantities. So this is called discrepancy. So this quantity is called discrepancy. Usually people take absolute value to really and ignore whether it's positive or negative. And so, okay. And we want to take our set to be small. So discrepancy is small. again, there are various kind of flavors in which kind of this problem comes. The flavor we are going to talk today is when we are want to this discrepancy to be always small. Okay, so not in some kind of average sense, like for most sets as it's small or some kind of things. No, we wanted it always to be small for today. So what I'm going to look is now then therefore the maximum over all such set S. So again, so what? But again, not literally all, because again this is too much. But all the kind of sets S which I care about. So all sets S that come from some family F. And again, F might be, family of all the actus parallel boxes or disks or whatever. Okay, so this is what's called discrepancy of this set P with respect to the family F. And I would like to find a set which is as evenly distributed in this set as possible. So, okay, so again, this will be the last definition for the pre-talk. Okay, if you hopefully this will not be it's not too overwhelming. So D and F, it's the discrepancy of the best set. So it's the smallest discrepancy among all sets P of this quantity dp. Okay, good. This is all definitions we're going to do right now. Okay, so let's just see that we are the basic results and basic questions about this, why we care about this also. Let me just explain that. Okay, so the basic case, and it's probably the most important case, is that F consists of all the axis parallel boxes inside the unit cube. Okay. Why people care about this is because of problem of numerical integration. Again, most. So what's the problem? Problem is you've got a function f, and you want to compute an integral of it. So, well, a function f is kind of function you see in calculus, like polynomial. Well, okay, well, we all TA calculus, or maybe taught calculus. Well, we should know how to do that. Okay, good. But most of the times out there in the wild, we don't want to integrate polynomials. We want to integrate some functions which have no closed form antiderivative. So fundamental theorem of calculus is of little use. So in that case, what is commonly done is, well, we're going to approximate this integral rather than compute it exactly. And how do we approximate it? Well, we're going to compute this function f at some points, and then we're going to aggregate those evaluations into some approximation of f. Okay. Of course, we need some kind of assumptions about f in order for this to work. For example, we will need to assume, okay, the function is not terribly discontinuous because, okay, well, clearly you're not be able to see anything, if it's, say, take some values, different values at your sample points and say completely different values elsewhere. Okay, so you need some kind of smoothness assumption on the function. I will not go into actual possible assumptions we can put on a function. There is a huge number of various results, but what they share in common is that if you put some kind of condition, maybe control some derivatives or some similar condition, then you can approximate this integral, provided that the sample points you choose have a low discrepancy, either in this definition or some closely related definition. Okay? So this is historically one of the main reasons why people care about discrepancy. Okay, the other being, these questions came from partly number theory, and people were interested basically how uniformly numbers can be distributed maybe modulo 1. And again, these are related actually, for example, to these higher dimensional notions after suitable transformation. Okay, but this is should kind of give you some motivation to pay attention to what I'm talking. Okay. So this is a problem. So what are the answers? So let me tell you the state of ignorance about this problem. So here is what's known, and this is long-standing problem. So this is okay, huge area. So discrepancy for the axis parallel boxes for this particular case. Okay, let me call this family I know boxes D. So BD is a family of all axis parallel boxes in D dimension. So that I can write it again and again. So discrepancy of boxes in D dimension. So there are two questions. Well, how good of a constructions can you find? And well, you can find better constructions, so give better and better integration methods. And on the other hand, showing that you cannot find better constructions than you already found. So let me tell you what constructions we know how to find. So the constructions we know how to find are of discrepancy, which is, okay, I will use the squiggly sign saying I will hide some constants, which I don't want to write. So, but up to some constants, we can find a set of discrepancy at most log n to the power d minus 1. So for example, in dimension 2, that's just log n. Dimension 3, it's log squared, etc. Again and again, there is a constant, again, which depends on d in this notation, which I actually doesn't have to depend on this particular result, but in general, this squiggly will mean some constant emitted. And maybe. Okay, this is an upper bound. The lower bounds, which again best known, look as follows. So we know a matching lower bound in dimension 2. So this bound is sharp in dimension 2. In dimension bigger than 2, it's an open problem. And the best exponent on a log we know is about half that. So, okay, so it's the log to the power right. The log to the power d minus 1 over 2. In some sense, this is okay. It's a relatively old result. Goes back to Roth. I mean, the same Roth who proved Roth approximation theorem, the same Roth who proved Roth's theorem of many progressions. It's the field's medalist Roth. So the lower bound goes to Roth, and it's again relatively uncomplicated. There are several ways to prove it, and again, it's clever, but again, you can expect a competent mathematician to find it eventually. This improvement in exponent, this was like a long line of relatively hard work by Beck, Baker, and most recently Belloc and Lacey. So again, this is hard. Getting this tiny improvement in exponent. Okay, this is for bigger than 3. Okay. Anyway, so this is the state of what we know. Okay, so I don't have an infinite amount of time to tell you everything about the discrepancy theory. So what I wanted to tell you is a result for a different family of sets, not the axis parallel boxes, which is somewhat related to kind of my main talk, which is coming in 30 minutes. And that's discrepancy for the convex sets. So it's the axis parallel boxes, convex sets. Okay, maybe before I do so, maybe people have questions, or jokes. Okay, all right. Well, I take the silence as encouragement. So let me continue. So let's again take, so again, so I will take this C2 because these are convex sets, family of all convex sets inside, okay, let me just put 2 dimensions. So inside a unit square. And so let me show you a lower bound on the discrepancy of point sets with respect to convex sets. So again, this is a much bigger family than just axis parallel boxes. Okay, it contains far more things than axis parallel boxes. So therefore you expect it to be much larger discrepancy, and indeed it is. So the correct order of magnitude is n to 1/3, and again this is sharp, but I'm not going to show the upper bound. Upper bound is substantially more involved than the lower bound. So let me show this. So it's a cute argument. So I've got a set P inside a unit square, and I want to show that there is a convex set where the number of points differs from expected by something large, like n to the 1/3. So, and how I'm going to find that set is I'm going to take a circle, so take an inscribed circle inside the unit square, and I'm going to tweak it. So it's going to be some modification of the units of the unit. Oh, sorry, not a circle. I misspoke. A disk. So take a unit disk. And I'm going to modify this unit disk, and this is going to be my convex set. Okay, this is my unit disk. So let me give it a name. So D is the disk in 0, 1 square, which looks like this. Okay, so it's not unit disk because this is correct. Its radius is 1/2, so it's okay. It's the inscribed disk. And I am going to consider small, what I would call flaps. So what's a flap? Flap is, okay, so I'm going to just basically draw things like this. So I'm going to just draw a chord inside this disk. And a flap is basically this region. It's this kind of a hat on top on this. And it's going to be super small. These flaps will be very small. So how small am I talking? Well, okay, so this dimension will be epsilon, but again, I'm being loose with constants. So really what I'm thinking is that the angle, so if I think about the center of my circle being here, what I'm really thinking is that this angle here is something like epsilon. Now, if this angle is like epsilon, then this length, well, it's twice sine of epsilon. Again, take Taylor expansion, or epsilon is small, take Taylor expansion of epsilon around 0. So it's about 2 epsilon. And again, I don't care about constants. So twice epsilon, epsilon. Okay, I'll just write it something like it's order epsilon. Now, what about the height in this picture of this flap? Well, if this is the sine, this is the cosine. Well, it's actually 1 minus cosine. Okay, and again, Taylor expansion of cosine has this 1 minus epsilon squared over 2. So this height is of the order epsilon squared. So I will write here epsilon squared. So this flap has area approximately epsilon cubed. Again, you can compute it exactly. It's but what I only care is between 2 constants times epsilon cubed. Because again, on one, it just contains we can see it's at least epsilon cubed because it contains a triangle where endpoint here, and endpoint here. And it's contained in a square, which is twice bigger. So epsilon cubed is what I say. So area is of the order epsilon cubed. Okay, so what's my epsilon now? My epsilon I choose to be so that the area, which is on the order of epsilon cubed, is equal, I mean, and again, literally equal, 1 over 2, 2 to n. Okay, so of course that means that my epsilon is something on the order n to the negative 1/3. Again, there's some constant here which I'm just too lazy to compute, and it's not going to matter for us. Okay, so this is what my flap is. And now, given a flap, well, what's the expected number of points which falls on a flap? Okay, let me make sure I haven't lost everybody. Okay, so what's expected number of points in such a flap? Okay, anybody?
Sorry, I haven't been keeping up, but it sounds like n times the volume.
Correct. So which is what?
One.
I mean, I put an equal. I didn't put a squiggly sign here. And this equal is important here.
Oh, well, then it's 1/2.
Correct. Yeah. So so the expected number of points is 1/2. So in particular, but actual number of points is not 1/2, right? It can be 0, it can be 1, it could be bigger than 1, but it's definitely not 1/2, right? So this is where we're going to get our discrepancy from, by the way. Okay. Okay. So the actual number of points will be not 1/2. It will be something else. So the way we take advantage of that is by breaking into cases. So the case 1 is that many of the flaps are emptied. So many of the flaps have 0 points, fewer points than expected. So, okay. By the way, how many flaps? When I say many flaps, what I'm going to do, sorry, I should have said it. I'm going to draw a bunch of disjoint flaps inside my disk. How many? Well, if the size of this is epsilon, again, I can put approximately 1 over epsilon of these flaps. So, okay, so what I'm saying, there are about n to the 1/3 disjoint flaps. So case 1 is that there are at least n to 1/3, at least half of the flaps are empty. At least n to 1/3 flaps are empty. Well, in that case, what I'm going to do, I'm going to take this disk and D, and I'm going to remove the empty flaps from it. And I'm going to get some set D prime. So it's basically a disk minus the empty flaps. The area of D prime, well, it's going to be the area of D minus the area of all of those flaps I removed. So I removed n to the 1/3 flaps, each of them of area of n 1 over 2, 1 over n approximately. So this is n to the 1/3 times 1 to n. So area has gone down by this much. On the other hand, the intersection with my set P has not changed because I only removed the empty flaps. So, well, in that case, it cannot be the discrepancy both of D and D prime is small because they contain the same points of P, but their areas are different, very different. They differ by n to negative 2/3. So that means the discrepancy of one of them must be large. So the discrepancy is large. And so this is case 1. The case 2 is the opposite case. many of the flaps are non-empty. At least half of the flaps are non-empty. So what we're going to do, we're going to remove the non-empty flaps. And again, so in that case, a similar calculation, which is again, I'll just do this an exercise for people who are curious. We'll show that, okay, since we removed at least 1 point from each of the flap, but the expected points, number of points we should remove was only a half per flap. So we removed too much. So again, either the regional set D or the D prime we obtained from it has a large discrepancy. So, okay, that's a proof of a lower bound. So again, construction is more involved. So again, I will not show you. Okay, we will see something similar in a different setting in the main talk. And again, okay, hopefully it was a short intro to discrepancy theory. Okay, and I'm happy to answer any questions or anything.
Does this kind of argument work for, say, 3 dimensions?
Yes. So for the convex sets, yes, I believe it does. I would need to refresh my memory, but definitely, I'm fairly sure it does give you correct bound. I mean, correct exponent. I'm fairly sure about that, but I will need to double check. Yes. It's the only case. It's easy to generalize it, just to consider some kind of flaps mechanism is joined. The difficulty is whether it gives the correct bound, and my memory tells me that it does, but I haven't checked before the talk. So.
Okay, thank you.
Where do you get the end of the 1/3 flaps are empty?
Oh, why there are so many flaps? Because okay, linear. So the flap has size epsilon, right? I mean, in this dimension, and epsilon. So thickness is epsilon squared. Width is epsilon. So imagine basically you are a small bug living on a surface of our surface of the unit disk, right? So what you're doing, you walk a distance epsilon, you make this flap, and then this is kind of a hole you dug in the ground. Then you keep on going, and you dig another the one of size epsilon, right? Because really the thickness is negligible. Again, I haven't. So really, okay, this angle is really epsilon, right? So basically, just need to proportional to epsilon. So that's it. So I have how many disjoint angles of size 1 of epsilon? Something like 1 over epsilon. Maybe some constant there because it's not. Again, this is approximation. So, but then my epsilon is end to the 1/3, so end to negative 1/3. So I get so many flaps. Yeah.
Wait. I still. How do we know that epsilon is end to the negative 1/3? We need the area to be 1 over 2n.
Correct. So okay. So if this was this trigonometry which I did not write down. So if my angle is epsilon, so this angle is epsilon. Now what is this distance? I wrote approximately epsilon, but really it is twice sine of epsilon. Right. This is just this distance is the from this distance here. So, okay, I'm looking at this angle. This distance here, the one I'm just highlighting right now, is sine of epsilon.
Which is approximately epsilon when epsilon is small.
So yeah, my epsilon goes to 0. So again, so my angle goes to 0. So this is basically 2 epsilon. So the sine of epsilon, again, its Taylor expansion is epsilon minus epsilon cubed times 3 factorial plus etc. Right? So again, epsilon goes to 0. It's basically epsilon.
Sure.
So order of magnitude, this is epsilon.
2 epsilon.
So basically, squiggly means I'm missing a constant. I'm not writing the constant.
I thought squiggly meant that the constant that you're missing is 1.
No, squiggly means in my talk, again, like a Humpty Dumpty. You know, my words mean what I want them to mean. So my symbols mean what I want them to mean, and in my talk, squiggly will mean I am omitting a constant. Okay, and what the constant will depend on, I will tell you if you ask me, but I'm omitting a constant. Okay, so this is of order epsilon. This height is of order epsilon squared. Same calculation instead of cosine, sine you get cosine. And expansion of that is 1 minus epsilon squared over 2.
Sure.
So the area is product of the height times width, again, times a constant.
Okay, I mean, like we can get the 1/2 and cancel out the 2, so the constant is actually 1. So okay, the area is epsilon cubed. Okay.
I mean, constant times epsilon cubed.
Okay, sure. So okay, epsilon is n to the negative 1/3. I still don't get how that implies that n to the 1/3 flaps are empty though.
Oh no!
Oh right, no, it's half of
case
them.
1. No, it doesn't imply so many flaps are empty. I'm going to look. I mean, what it implies is that there are so many disjoint flaps, and then I'm going to look at those flaps and ask, are most of them empty, or most of them are not empty? So what I done on the board is the case that most of them are empty. And there is another case which I didn't write on the board, which is most of them are not empty. I mean, the two cases are very similar. And I can. Does it answer your question? Alex, I believe?
Yes, sorry.
Okay, no, because I see the label. But some people, you know, like mislabel themselves by accident.
No, that is my name, yeah.
Okay.
Sorry.
Okay, I forgot to mention the camera automatically shuts off every half an hour. I need to turn it on back on. That's to prevent. Okay.
Sorry for asking all these questions. I missed the first 5 minutes, and so I was talking with people in the chat trying to figure out what discrepancy is in the first place. So
no, look, I mean, again, it's good to ask questions. I mean, this is good. I mean, otherwise, you know, you can and should, you know, just read the book, you know, right? You know, like the whole point of people, you know, of a seminar is that it's interactive, because otherwise, look, I'm not going to do as well as a well-written book, you know, which got through a couple of editions and several years of revisions, right? I can't. I will make more mistakes and I will omit things, etc.
Okay, if there's no more question, I mean, feel free to ask afterwards, but let's take the chance to unmute yourself and thank our speaker for this nice pre-seminar.
I do have another question though.
Yeah, but can we clap first?
All right.
Yeah, go ahead, Alex.
So what does removing the empty flaps do?
What removing empty flaps does, it changes the area of the set. So
without changing the number of points included, correct. Sure.
Correct. So, you know, if original disk had small discrepancy, it got really the expected number of points, then after the set we obtain after removing flaps certainly does not have this property, because it has taken the same number of points. But
I see. So it's a lower bound. Oh, yeah. Okay.
Okay, so it cannot happen that both the original set and the new set have low discrepancy.
I see. And the reason that we do it with these flaps is to make sure that both the original set and the new set are convex.
Correct. Very good. I should have mentioned it. Thank you. Yes. And this is why we cannot find more of them, because otherwise, you know, the convexity gets in the way. Yep. Very good.
Thank you.
You're welcome.